Okay, so that's the foundation model. So hopefully, if you get interested in this field, right, so you can using this kind of pre-training approach, right? If you have a large amount of data, you have a different types of data, right? You can train this kind of foundation model, and then this model can be easily adapted to different downstream tasks. Okay. And the second topic I want to discuss is the transparency of deep learning model. So this is very important, especially for medical or healthcare domain, right? Because anything coming from the AI or machine learning model, we need to have some explainability, right? The transparency of the model, right? Why this and how this model reached such conclusion or decision. So this model transparency refer to the ability of the deep learning model to explain how it arrived at a certain decision or prediction, right? And it is very crucial to build trust and the confidence in the result, right? You're able to kind of explain, right, why the model make the prediction. And for the medical domain, right, so we can using this to do the medical diagnosis. Right, the transparency of the deep learning model is very essential, right, to understand the factors that contribute to a diagnosis. Right, if the doctor using AI to help them to make diagnosis, right, they need to know, right, why this what kind of factors or what kind of basis this AI model make decision. Is going to be accurate based on his or her domain knowledge, right? And also for the medical prognosis, right? So this also can help medical professionals to identify the most effective treatment and intervention for patients, right? So this will ultimately improve the patient outcome, okay? So as in our previous lecture, when we talk about deep learning, right? So we talk about a little bit about the interpretability or explainability of the machine learning model or deep learning model in particular. So there's a couple of ways we can do that, right? So one is we can visualize the filter. So here example shows the filters or kernels at different CNN layer, right? So that's one simple and straightforward way we can visualize these and maybe make some of the interpretation. And we also talk about, right, we can using maybe the last layer, right, as the feature embedding and do the nearest neighbor retrieval, right? So for the test image, right, we extract the feature maybe from the last layer, a fully connect layer, right, as the feature embedding, and we use that to retrieve the nearest neighbor, and we get a sense, right, if this model make the accurate prediction, right? So these examples are kind of can tell that, right, the model is able to retrieve similar semantic or concept. And another way is we can do this kind of visualization, right? We do this dimensionality reduction, right? The original feature embedding, right, for like the FC layers are high dimension in the high dimension. So we can do dimension reduction, and then we can visualize these features, right? So here, this TSNE, or maybe you can just simply using the PCA to reduce the dimension, and we can see from the data set, right, how these features from different samples are kind of distributed, right? Maybe some of them are clustered into different clusters, right? So we can using this to interpret. And for image for image processing, the most important or widely used one is using the so-called class activation map, right? So we also mentioned that when we explain how this CAM is able to figure out or understand, right, what this CNN is looking at, right, to make such decision. So here, just a quick recap, right? So basically, we have this network to generate these features, right? And after we can do the global average pooling, right? Basically, collapse each of the feature map into a single neuron, right, to a single scalar, and then have a last layer, have the fully connected layer with the weights, and we can generate the final class probability output, right? And for each of the class output, then we can go back and generate like a weighted feature map. And this weighted feature map is able to identify, right, the region where the network is focused the most, right? The decision made is mostly focused on these particular region, right? This is the class activation map to highlight the pixels or regions from the image, okay? So this is a couple of example we showed. So for different type of output, right? And this is how the network is focused on, right? Different regions the network focused on to get this corresponding prediction. And we also talk about the improved version, right? The grading cam, right? So in this case, grading cam does not rely on global average pooling. So that's one limitation of the cam. So the network has to rely on the global average pooling. And for some architecture, if they don't have GAP, they have to incorporate that and maybe retrain the model. So grading cam can alleviate that, mitigate that limitation, and also give maybe more accurate localization of the important region for interpretation. Okay, so this is very important in medical image processing, right? So a lot of time we have to do the explanation or trying to understand, right, why the model maybe classify this is a tumor, or maybe classify there is some anomaly. So we can look at the pixels or the most active region, right? This network is focused on. Okay. We also have a work that is developed not only for the classification, but we also do this for image matching problem. Okay, so this is kind of like a retrieval task, right? So you have a given image, you want to find a match image in the database. So this is basically doing the metric learning. So we also want to explain this, right? So for this example here, we are doing image retrieval, right? So doing this kind of cross view image retrieval. So for the input is the query, right? So we have a street view image. And I think there's someone didn't mute. Could you please mute? Okay, thank you. So the input is the query street view image, right? So, and the database, the reference is the satellite view, right? So the satellite images, okay? So we want to find the correct match, right? So these are corresponding to the same GPS location, okay? And we can develop this kind of retrieval or image matching the framework, right, or network. And eventually, we also want to do some explanation, right, why these two images are considered a match, right? So we extend this grading cam approach to this metric learning paradigm, okay? And then we can explain, right? So if we look at these example, right, the model say this is the top ranked image, and we can using our develop approach to explain why this is the case, okay? So we can actually visualize, right, for this to be considered a match, we can actually examine, right, what region contribute the most to the similarity measure, right? We'll say the network predict there's a similarity measure of 0.8, okay? And we can see what region contribute the most to this 0.8 similarity, right? So here, the visualization tool is able to highlight this house region, right? If you go to the satellite image, it's actually corresponding to the house, this particular house in the satellite view, okay? So this give us a sense, right? What kind of information this model is actually using to make to do this matching, right? So these are two views has a very large visual discrepancy, right? One is street view on the side of the building, the road, but on the other hand, the satellite image mostly focused on the top, right? Only the rooftop or maybe the layout of particular location, okay? And our method also can do this kind of point-wise, explanation, right? So if you can see the dot, right, the red dot is actually moving around this image, right? At each of the location, we can generate the corresponding kind of activation map, right? What region in this reference image, this satellite view, correspond the most to this particular point, right? So here we're actually able to see how this kind of activation map change at different locations. Okay, so the cross-view image retrieval or matching is one particular application for metric learning. So other metric learning is we can do face verification, right? We want to match, have a query, right? Have a reference, which face image corresponding to the query, right? Maybe they corresponding to the same identity. We can also do person re-identification, right? Basically also like a matching problem. You have a query person, then you want to identify one, the same person in the reference database. We can also, we can all using this developed method to explain, right, why these two image are considered a match, right? What kind of region are focused, right? For person ID, maybe the model focused on a specific, like a backpack. If they have the same backpack, they're using that cue to make the decision. Or maybe the clothing, or maybe specific object, right, to make the decision. So we can do this kind of interpretation using this method, okay? So if you're interested, you can check our paper and the code is also available, okay? So here I list more reference in terms of a transparency of the deep neural networks, and also specifically for medical image analysis. So you can check out these survey or papers for some details, okay? Finally, I also want to briefly mention about these generative machine learning models, which I think all of you guys believe they getting a lot of attention in the AI world, right? So the general models are basically a class of machine learning models, designed to learn the underlying distribution of a data set, right? So if you're able to learn a distribution of the data, right, then you can using that to generate any new data points, right? So that's the idea of the generative model, right? Learn the distribution, then you can using that to generate a lot of data, okay, which fits the original, distribution. So some of the classic models or methods, right? Again, general adversarial networks, right? And also these variational autoencoder. And we'll also have some flow-based models. And the reason we have these, diffusion models, right? Getting a lot of attractions and using a lot of applications using diffusion models, right? Text to image, image to image translation, text to video, right? Image, video editing, etc. Right? So you can see a lot of applications starting to using diffusion models. Okay, but definitely we can see there's a lot of benefits for these kind of generative model, right? Generating the data, right? So for some of the application, right, especially applications that don't have a lot of training data, then this kind of generative model is able to provide a very effective tool to generate the data and the corresponding label easily to train the model, right? So that's one significant benefit for these generative models. But the downside is that there's also maybe potential risk, right, for these kind of generate data. So there's one research area called deep fake, right? Basically, you can generate very realistic fake images and videos, but not for the good use, right? Maybe trying to do some even crime, right? To generate videos or some of the images that maybe to fool maybe someone's relative or families, right? For some of the financial crimes that's possible. So here I want to show you one video. So the video was generated, and let's take a look. Okay. So So this is
So let's check this out first.
Deep learning from MIT.
MIT. Here at MIT. Deep learning is revolutionizing so many fields, from robotics to medicine and everything in between. You'll learn fundamentals of this field and how you can build some of these incredible algorithms.
Okay, so this is the like a demo video built by Alexander, right, for this introduction to deep learning course. When he talk about some of the potential risk of deep learning model, of this generative model. And you can see from this video, right, we can definitely tell this is fake. Maybe some of the audio information will give away, right? But if you look at details, some of the lip movement is actually very realistic, right? The sentence, is kind of sync with the lip movement, right? Without some of the audio information, you may feel like this is like a real video, but for the audio information, definitely there's some, inconsistency. We can tell that maybe this video, at least the audio has been fabricated. Okay. So this is how they generate this kind of demo video, right? So you have a input audio, right? Then you can also doing this kind of mouse synthesis, right? First from the key point, right? Trying to get this motion of the lips moving, right? And also you can put this into a target video. So basically you have a real video with the former President Barack Obama, giving a speech. But here the idea or the goal is take that real video, maybe change the lip region, right? Based on the given input audio, right? This is totally different than the original audio from the video, but you want to make it, or incorporate that into this target video. So you want the lip region, right, to sync with this input audio and feel like this entire video, right, the appearance and the audio information, they are able to sync with each other and everything looks realistic. Okay, so that's how they generate this kind of fake video to do the demonstration. Okay. But here, our goal is we want to detect or identify these fake image as a video, right? So a lot of, like social medias, right? You post these images and video, and now we have to be concerned about, right? Is this image or video real, right? Because AI is able to generate very realistic images and video that we may not able to identify by human eyes, right? So we need to rely on, again, on AI to detect this kind of fake images and video. So here, this paper specifically, develop approach to detect these fake images and video. The method they are using is trying to look at the information in the spectrum domain, right? Here, this is the real image, right? You can do some transformation, right, in the frequency domain, right? You can using the Fourier transform, or maybe using wavelet or DCT transform. So Fourier transform is very popular, easy to use. So they using the Fourier transform and get into the spectral domain and analyze these, the signals in the frequency domain, right? And here, this is the image, right? The horse image was generated by the AutoGAN or reconstructed by AutoGAN. And they are able to, spot some of the artifacts in the spectral domain, okay? So here they provide a list or a couple of examples, right? So the first row is the synthetic image, right? The generated image. You may not able to identify or detect they are fake, but if you go to the frequency domain, right, doing the Fourier transform, and you look at the spectrum, and compare with the original real image, right? So the generated or fake image has a lot of artifacts, right? So using in the frequency domain, right, this kind of fake image can be easily detected, right? We can basically come up with some method, right, to maybe measure or to detect a specific artifact in the frequency domain. Okay, so that's their approach in doing this kind of frequency analysis. And another approach is they kind of inspired by this kind of RPPG, remote PPG estimation, right? So basically we can estimate some biological signals, right? Like the heart rate, heartbeat from the videos, right? There's an approach, right? We can extract the information from the face, right? Basically, because of the blood flow, right? So, blood pumping to different body parts, and this will have small, different changes into the color of the skin. Okay, maybe this is not able to easily identify by the eye, but this can reflect something into the pixels, right? So the pixel changes, and we can actually extract those informations and trying to identify or predict the heart rate. Okay, so if this is a real video, right, we do using some of the RPPG approach to estimate the heart rate, and we can get something that's similar to like the measure come from the the ECG, right? And so if this is a fake video, right, on the bottom, so this is the fake video, and because this is a video and they may do this in a frame basis, it's going to be some of the temporal inconsistency, right? So there's going to be some artifacts. Maybe as frame, there's a color fluctuation a lot, or maybe some of the shape will change a little bit, right? The hairstyle change a bit, or the shape of the eye or nose or their placement, their position will change a bit. So this will also affect the PPG signal estimation, okay? So they basically can do using a training set, right, contain the real video and also the fake video, and trying to estimate these kind of biological signals and using this as a mechanism to detect, right, if this is a real video or fake video. Okay, so that's I think a very interesting technique, trying to using this biological signal as a way to detect if this is a real video or fake video. Okay. Okay, so this is some of the illustration. So for details, you can refer to their paper, and if you're interested, you can check more details in that paper. Okay. Okay, I also provide 2 surveys, right? The creation and detection of deep fakes, right? Some of the method, right? How can you generate deep fake, right? Like very realistic images and video, and what other kind of detection methods, right? We're able to detect those fake or synthetic image. Okay.